Hello everyone, good morning, good afternoon and good evening. Today our first topic, laws of chemical combinations, and this is a part of some basic concepts of chemistry. In some basic concepts of chemistry, the first topic is laws of chemical combination. So in this lecture, all laws of chemical combinations and their important MCQs, important questions we are going to discuss. For each and every law, we are going to discuss important questions. So anyway, here 6 laws are there. 6 laws. Laws of conservation of mass, law of definite proportion, law of multiple proportion, law of inverse proportion, Avogadros hypothesis, Gay-Lussacs law of combining volumes. So the combination of all the 6 laws is Dalton's atomic theory. Dalton proposed his atomic theory based on these 6 laws. At last, we will discuss Dalton's atomic theory also. Right. So exactly what is laws of chemical combinations? How elements are combining and how elements are giving compounds. So that is explained by laws of chemical combinations. The combination of elements and formation of compounds is explained by laws of chemical combinations. Of course, some limitations are there. We will discuss limitations also. Our first law is law of conservation of mass. So what is law of conservation of mass? Mass is neither created nor destroyed. In simple words, I am taking a reaction. R gives rise to products, where R is reactant and P is product. So according to law of conservation of mass, the mass of total mass of the reactants before reaction is equal to total mass of the products. This is law of conservation of mass. Mass is neither created nor destroyed in any chemical reaction. For example, I have a reaction C plus O2 gives rise to CO2. What is the mass of carbon? Carbon mass is 12 grams. Oxygen mass is 32 grams. And what is the mass of carbon dioxide? Carbon dioxide mass is 44 grams. How do you say carbon dioxide mass is 44 grams? Sir, carbon is 12 grams. Oxygen is 32 grams. Total mass is 44 grams. So definitely carbon dioxide mass must be 44 grams. So to answer the mass of carbon dioxide in this chemical reaction, I am using law of conservation of mass. If there is no law of conservation of mass, I cannot use this relation. Say what relation I have used here? Total mass of the reactants before reaction is equal to total mass of the products after reaction. So there is an exception for law of conservation of mass. In chemical reactions, there is no exception. But in nuclear reactions, all nuclear reactions are exception for law of conservation of mass. You take any nuclear reaction, nuclear fusion, nuclear fission, in any nuclear reaction, the total mass is not converted into products. There is some difference in mass of products to mass of reactants. That difference in mass is called mass defect. So this mass defect is converted into energy. That energy is called as binding energy. So 1 AMU, 1 unit mass is converted into 931.5 million electron volts energy. Right? In nuclear reaction, some amount of mass is lost. That energy is converted into, that mass is converted into energy. So law of conservation of mass is not applicable for nuclear reactions. It is applicable only for chemical reactions. Even in chemical reactions, for example, take A gives rise to B. A gives rise to B. Assume this is highly exothermic reaction. A gives rise to B. This is highly exothermic reaction. Large amount of energy is released in the conversion of A into B. So as per the thermodynamics, how do you say this reaction is exothermic? So exothermic means delta H value is negative. Exothermic means delta H value is negative. So delta H value is negative means the enthalpy of products is less than enthalpy of reactants. So what I am trying to say here, product's energy is less than reactant's energy in exothermic reactions. Product's energy is less than reactant's energy in exothermic reaction. Right? Some amount of energy is released. Some amount of energy is released. From where it is getting energy? Even in chemical reaction, some amount of mass is lost, but that mass is negligible. Even in chemical reaction, and a mass is lost, that mass is converted into energy. So this energy is coming from the mass only, but the mass lost is negligible and this energy lost is negligible compared to nuclear reactions. In nuclear reactions, huge amount of energy is released. So that's why the mass is considered. The loss in mass is considered in nuclear reaction. But in chemical reactions, the energy released is less compared to nuclear reaction. So the loss in mass is not considered, that is negligible. So it is not an exception. Only nuclear reactions are exception for law of conservation of mass. So based on law of conservation of mass, one important question. 4.2 grams of sodium bicarbonate is added to a solution of acetic acid weighing 10 grams. So I am taking sodium bicarbonate. This is mixed with acetic acid. And what is its product? Sodium acetate, water and carbon dioxide. This is the reaction. So in this reaction, sodium bicarbonate is 4.2 grams. Acetic acid is 10 grams. So total mass of the reactants 14.2 grams. Total mass of the reactants 14.2 grams. The residue left behind is found to weigh 12 grams and 2.2 grams, 2.2 grams of carbon dioxide is released. Say carbon dioxide how much? 2.2 grams. Then residue mass is what? 12 grams. What is the residue? Sodium acetate and water together 12 grams. What is the total mass of the products? 14.2 grams. So total mass of the reactant is 14.2 grams and total mass of the product also 14.2 grams. So this is according to law of conservation of mass. Right? In any chemical reaction, total mass of the reactants is equal to total mass of the product before and after reactions. So another important question. According to law of conservation of mass, for a chemical reaction involving multiple steps to form a product P from reactants A and B. So these are the reactants. From reactants A and B, product P is formed. Right? Which statement is true regarding the net mass change considering any mass energy equivalence? Right. So they asked to find what is the correct statement in this. Right. So first statement is total mass of reactants A and B must exactly equal to final total mass of product P. This is correct statement. Next, the mass of product P can be significantly greater than mass of reactants A and B. This is wrong statement. Total mass of reactants A and B must equal to final total mass of products plus energy equivalent of mass. No. So this is applicable in nuclear reactions. It is not applicable here. So mass changes only in nuclear reactions. So option A applies to all chemical reactions. This is correct statement. Right? So statement A is correct and statement D is also correct. Coming to next law, law of constant or definite proportion. A given compound contains always same elements in a fixed proportion with a definite proportion. Right? For example, I am taking water. Example, water. Whatever the method of preparation of water, any method you take, In all the methods, the sample of water contains hydrogen and oxygen. There is no other element. So use combustion of hydrogen, which gives water, or acid base reaction, HCl plus NaOH, NaCl and water. Like this, any chemical reaction, any preparation method you take for the preparation of water, all the samples of water contains hydrogen and oxygen, and the hydrogen and oxygen are combining in a different proportion. Take this H2O. Hydrogen mass is 2 grams, oxygen mass is 16 grams. What is its mass ratio? 1:8. So whatever the method of preparation, the given compound always contains same elements and their mass ratio is different ratio. It's a fixed ratio. Suppose carbon dioxide, take carbon dioxide. Any method you take for the preparation of carbon dioxide. So that carbon dioxide contains carbon and oxygen and the mass ratio is fixed, that is 3:8. Carbon mass is 12 grams, oxygen mass is 32 grams, so 3:8 ratio. So this is law of constant and law of definite proportion. So there is an exception for law of constant proportion, that is non-stoichiometric compounds. So exception for law of constant or definite proportion is what? Non-stoichiometric compounds. So these non-stoichiometric compounds, they don't follow any fixed ratio. So that is why it is an exception for this constant proportion. See example, Fe 0.84O, generally ferrous oxide and ferric oxide. Ferrous oxide is FeO, ferric oxide is what? Fe2O3, right? But here what is the composition? 0.84 and 1. So this fractional composition of the compounds, the compounds with fractional composition are non-stoichiometric compound. They don't follow laws of chemical combinations. Similarly, titanium 0.7O is an exception and it is a non-stoichiometric compound. So based on law of constant proportion, one important question. Two gaseous samples were analyzed. One contained 1.2 grams carbon and 3.2 grams oxygen. Carbon 1.2 grams and oxygen is 3.2 grams. Right. In the other case, carbon contains 27.3%, oxygen contains 72.7%. So we have two samples. In these two samples, the elements are carbon and oxygen. First sample carbon and oxygen, second sample also carbon and oxygen. Right. So here carbon mass is 1.2 grams, oxygen mass is 3.2 grams. Similarly, in the second sample, carbon percentage is 27.3%, oxygen is 72.7%. Now we have to prove that it satisfies law of constant proportion. Simple. So take the mass of carbon divided by, or take mass of oxygen divided by carbon. Mass of oxygen divided by carbon. So this is 3.2 grams. This is 1.2 grams. How much will get? This is 8 by 3. 8 by 3. So this ratio is what? 8:3. 8:3. Now take oxygen percentage divided by carbon percentage. Oxygen percentage is how much? 72.7. Carbon percentage is 27.3. Simplify this, you will get 8 by 3. 3 nines, 8 nines, 8 by 3. Here what is the ratio? 8. So we have two different samples. Both samples are having carbon and oxygen and their mass ratio is same for both. Then that is the same compound. So for same compound, different samples, but it is the same compound. How do you say it is same compound? The elements are same and the ratio is also fixed. So this is according to law of constant proportion. law of constant or definite proportion. Next, law of multiple proportions. When two elements form more than one compound, the different masses of one element that combine with a fixed mass of the other are in the ratio of small whole numbers. What is law of multiple proportion? I have two elements. When two elements combine to form two or more compounds, when two elements combine to form two or more compounds, the ratio of masses of one element with respect to second element is in simple whole number ratio. That is what law of multiple proportion says. So let us take simple example. I am taking two elements, carbon and oxygen. When carbon combines with oxygen, two different compounds are possible, CO and CO2. Two compounds are possible, CO and CO2. It depends on valency. If any element exhibits variable valency, it gives many compounds. For example, nitrogen and oxygen. Nitrogen has variable valency. So when nitrogen combines with the oxygen, it forms many compounds. NO, N2O, N2O3, N2O5. We will take that example also. Right. So here carbon valency is 2, compound is CO. This carbon valency is 4, compound is CO2. Now, what is law of multiple proportion? Let us take their weights. In CO, 12 grams of carbon is combined with 16 grams of oxygen. In CO2, 12 grams of carbon is combined with 32 grams of oxygen. So what law of multiple proportion says? For the fixed mass of one element, find the ratio of masses of other element. So I will take carbon as fixed. 12 grams carbon as fixed. Then I will find the ratio of masses of oxygen in both CO and CO2. So for 12 grams of carbon, what is the ratio of masses of oxygen? 16 is to 32. 16 is to 32 means 1 is to 2. So 1 is to 2 ratio is a simple whole number ratio. It is a simple whole number ratio. So 1 is to 2, 2 is to 3, 3 is to 4, or 2 is to 5. So all these are simple whole number ratios. We don't get heavy numbers, we don't get fractional ratios. So except fractional and heavy numbers, remaining all ratios are simple whole number ratio. So when two elements combine to form two or more compounds, for the fixed mass of one element, the ratio of masses of second element is always in simple whole number ratio. So this is law of multiple proportion. Another important example for law of multiple proportion. Nitrogen and oxygen. Combination of nitrogen and oxygen. When nitrogen combines with oxygen, many compounds will be formed, many oxides will be formed because nitrogen has variable valency. Nitrogen shows variable valency. I mean valency 1, valency 2, valency 3, valency 4, valency 5, like that. It shows many variable valencies. So their compounds are nitrous oxide, nitric oxide, nitrogen sesqui oxide or dinitrogen trioxide, nitrogen dioxide and nitrogen pentoxide. In nitrous oxide, 28 grams of nitrogen is combined with 16 grams of oxygen. Nitrous oxide is laughing gas. Nitric oxide, 14 grams of nitrogen is combined with 16 grams of oxygen. Nitrogen sesqui oxide, 28 grams of nitrogen is combined with 48 grams of oxygen. There are 3 oxygen, each oxygen 16. In NO2, 14 grams of nitrogen is combined with 32 grams of oxygen. In N2O5, 28 grams of nitrogen is combined with 80 grams of oxygen. 5 oxygen, 5 16s are 80. According to law of multiple proportion, for a fixed mass of one element, the ratio of masses of The other element in all the compounds is simple whole number ratio. I will take 14 grams of nitrogen as fixed. Now we should find mass ratio of oxygen for 14 grams of nitrogen. Here 20 grams of nitrogen is combined with 16 grams of oxygen, but we want 14 grams nitrogen for 14 grams of nitrogen. So here I am taking nitrogen as fixed. You can take oxygen as fixed also. Take oxygen fixed mass and find the ratio of masses of nitrogen. You will get simple whole number ratio. I am taking nitrogen mass as fixed, that is 14 grams. So for 14 grams of nitrogen, how much oxygen is there? Half, that is 8 grams of oxygen. Second compound, for 14 grams of nitrogen, 16 grams. So this is fixed mass. So 16. Next. In N2O3, for 28 grams of nitrogen, how much oxygen is there? 48. For 14 grams, it is 24, half of that. For 14 grams, here this is direct, 32. 28 grams is there. So I should calculate for 14 grams. Half of this 28, 14, half of the 80, 40. Now take the ratio of all these numbers. So 1:2, 2:3, 4:5. So this is a simple whole number ratio. So nitrogen and oxygen are following the law of multiple proportion. Next, based on law of multiple proportion, a simple question. The law of multiple proportion was observed for the following pair. Here, small trick is whenever two elements are combined, or the complete problem is in terms of two elements, just two elements, no doubt that is law of multiple proportion. If the given problem is revolving around three elements ABC, three elements hydrogen, oxygen, sulfur. So the problem is discussing with three elements. That concept is law of reciprocal proportion or law of inverse proportion. But this is what? Law of multiple proportion. See here, carbon, oxygen, nitrogen. Wrong answer. Law of multiple proportion means it should have only two elements. Nitrogen, oxygen, correct. Hydrogen, oxygen, hydrogen, sulfur. Hydrogen, oxygen, sulfur, three elements, wrong. Hydrogen, sulfur, oxygen, three elements, wrong. So our answer is N2O and NO2. So law of multiple proportion means it should deal with only two elements. So another important question from law of multiple proportion. The mass of nitrogen per gram hydrogen in hydrogen is exactly 1.5 the mass of nitrogen in the compound ammonia. The fact illustrates that. Means it is law of conservation of mass or law of multiple proportion or law of constant proportion. Which law? It is following which law? That is the question here. Now, in this we have two compounds. One is hydrogen, N2H4. Another compound is ammonia, NS. In hydrogen, 28 grams of nitrogen is combined with 4 grams of hydrogen. In ammonia, 14 grams of nitrogen is combined with 3 grams of hydrogen. So here 1 gram of hydrogen is taken as fixed. In the given question, 1 gram hydrogen is taken as fixed. So for 1 gram hydrogen, what is the mass of nitrogen? 28 by 4, which is equal to 7 grams. In ammonia, for 1 gram of hydrogen, 14 by 3 grams of nitrogen is there. So for the fixed mass of 1 gram hydrogen, so 1 gram hydrogen is fixed. For the fixed mass of 1 gram hydrogen, find the ratio of masses of nitrogen in these two compounds, that is 7:14 by 3. So 7:14 by 3 means that is 1:2 by 3, and this ratio is what? 3:2. 3:2 is a simple whole number ratio. So this problem is following the law of multiple proportion. So 3:2 means 3 by 2. 3 by 2 means 1 by 2. So the mass of nitrogen in hydrogen per 1 gram of hydrogen is 1.5 mass of the nitrogen in the compound of ammonia. Whatever it is, the given data is satisfying the law of multiple proportion. Next one is law of inverse or reciprocal proportion. When elements A and B form compounds with C, the ratio of A and B that combine with a fixed mass of C is a simple multiple ratio in which A and B combine with each other. Simple. We have three elements A, B, C. Out of three elements, find the mass ratio of two elements with respect to fixed mass of third element. Find the mass ratio of A, B elements with respect to fixed mass of C. That is one ratio. And next, the second part is when those two elements A and B combined directly with each other. A and B combined with each other directly. Find its mass ratio, mass ratio of A and B. So those two ratios must be in a simple whole number ratio. This is what we call reciprocal proportion. So let us take example. I am taking hydrogen, oxygen and carbon. Hydrogen, oxygen, carbon. Three elements. So arrange these three elements in the corners of this triangle. So I will take hydrogen here, oxygen here, carbon here. Anywhere you can take. There is no fixed rule. Hydrogen must be taken at top. There is no fixed rule. Anywhere you can take. When hydrogen and oxygen combine, it will give us water. When hydrogen carbon combine, it will give methane. And carbon and oxygen combined, it will give carbon dioxide. So first, let us discuss these two, water and methane. Right? Here, 1 gram hydrogen, I will take fixed mass. 1 gram of hydrogen as fixed mass. We can take oxygen as fixed, carbon as fixed, anything as fixed. I am taking hydrogen as fixed, that is 1 gram. Right? So in water, 16 grams of oxygen is combined with 2 grams of hydrogen. So in water, 16 grams of oxygen is combined with 2 grams of hydrogen. So I want for 1 gram. So 1 gram hydrogen is combined with 8 grams of oxygen. So this is mass of oxygen for 1 gram of hydrogen. Similarly for methane, 12 grams of carbon is combined with 4 grams of hydrogen. For 1 gram of hydrogen, what is the mass of carbon required? That is 12 by 4. 12 by 4 means what? 3 grams. 3 grams of carbon. Now, first ratio. The mass ratio of oxygen and carbon with respect to fixed mass of hydrogen, that is 8:3. Oxygen mass is 8 grams, carbon mass is 3 grams, that is 8:3. Now, second part is what? When those two elements, carbon and oxygen, directly combine with each other, find their mass ratio. Here, when carbon and oxygen combine together, the product is carbon dioxide. So, carbon 12 grams, oxygen 32 grams. So, what is the total mass ratio? 3:8. So, oxygen and carbon mass ratio 8:3. So, these two ratios are a simple whole number ratio. Once again, we have three elements, hydrogen, oxygen and carbon. For a fixed mass of hydrogen, I am finding the mass ratio of carbon and oxygen. That is what? 8:3. Oxygen and carbon mass ratio is 8:3. Now, when oxygen and carbon are directly combined with each other, their mass ratio, oxygen and carbon mass ratio is what? 8:3. So, both ratios are simple whole number ratios. So, no need to be same. No need to be same. In some cases, the mass ratios will be same. In some cases, mass ratios will be different. But the rule is what? There should be simple whole number ratios. Question related to law of reciprocal proportion. One part of an element A combines with 2 parts of another element B. 6 parts of element C combines with 4 parts of B. If A and C combine together, the ratio of their weights will be governed by. Simple. When if the problem is discussing with two elements, that is law of multiple proportion. And here in this problem, they are discussing about three elements. So three elements means law of reciprocal proportion. Answer is law of reciprocal proportion. So law of reciprocal proportion. So let us discuss in detail. So there are three elements A, B, C. Three elements are there. A combines with A is combined with two parts of B and 6 parts of C is combined with 4 parts of B. Now I will take B as fixed. B one part as fixed. Take B as fixed, that is one part. Now for one part of B, how much A is there? A by 2. For one part of B, how much C is there? 6 by 4. 6 by 4 means that is 3 by 2. So for the fixed mass of B, mass ratio of A and C, mass ratio of A and C, what is that? 1 by 2 is to 3 by 2. What is this ratio? 1 is to 3. This is our first ratio. And second ratio, what we have to do? Direct combination. Now first case, with respect to B, we have calculated the ratio. Now second case is what? When A and C are directly combined. A and C are directly combined. So that is 1 is to 6. One part of A and 6 parts of C. So this direct combination is giving 1 is to 6. So here ratio is 1 is to 3. Here ratio is 1 is to 6. Both are simple whole number ratios. So this data is following the law of reciprocal proportion, and this much calculation is not required because when three elements are there, that is law of reciprocal proportion. When two elements are there, that is law of multiple proportion. This is simple trick. Now coming to next law, Gay-Lussacs law of combining volume. A statement is at constant temperature and pressure. At constant temperature and pressure in a gaseous reaction, the ratio of volumes of all reactants and products are in simple whole number ratio. If products are also gases, then reactants volume and product volumes ratio is simple whole number ratio. Suppose product is not gas, only reactants are gases, then you can take reactant volumes, right? So at constant temperature and pressure, the ratio of volumes of all gaseous reactants and products are in simple whole number ratio. For example, I am taking N2 plus 3H2 gives rise to 2NH3. We know nitrogen is a gas, hydrogen is a gas, ammonia is also gas. As per this reaction, this is a balanced reaction. As per the reaction, nitrogen is 1 mole, hydrogen is 3 moles, and ammonia is 2 moles. So 1 mole means its volume. Let us take it as 1 volume. It has STP 22.4 liters. It's fine. I am taking 1 mole, 1 volume. This is 3 volumes. Ammonia is 2 volume. Take the ratio. So that is 1 is to 3 is to 2. It's a simple whole number ratio. So in this reaction, all reactants and products are in gaseous state. So the ratio of their volumes is 1 is to 3 is to 2. It's a simple whole number ratio. For example, C plus O2 gives rise to CO2 is there. Here carbon is solid, oxygen is gas, carbon dioxide is also gas. Here carbon is solid, we don't take its volume. Only gases, reactants and products we have to consider. What is its ratio? 1 is to 1. 1 is to 1 is the volume ratio. On hypothetical reaction, A plus B gives rise to C is there, where C is solid and A is solid and B is gas. See, here only one gas is there. Here, Gay-Lussacs law of combining volume is not applicable because only one gas is. At least two gases, reactants or products are there. We can apply Gay-Lussacs law of combining volumes. Now, one question based on Gay-Lussacs law of combining volume. Here, 20 ml of hydrogen gas reacts completely with 10 ml of oxygen gas to produce water vapor. What volume of water vapor is formed at the same temperature and pressure? See, take hydrogen. Hydrogen is combining with oxygen to produce water. Balance this reaction. 2H2 plus O2 gives rise to 2H2O. Hydrogen gas volume is given as 20 ml. Oxygen volume is 10 ml. And what is a water volume? So this is not law of conservation of mass. Law of conservation of mass means what we will do. So the mass of total mass of reactants before reaction is equal to total mass of products after reaction. So it is not law of conservation of mass. It is Gay-Lussacs law of combining volume. Here 2 moles 20 ml, 1 mole 10 ml. Here 2 moles you will get 20 ml. It's not 30 ml. It's not 30 ml, right? 2 moles of hydrogen to 1 mole of oxygen is combined to give 2 moles of water vapor. So 20 ml of water is formed. This 20 ml is based on Gay-Lussacs law of combining volumes because take the ratio. That is what 20 is to 10 is to 20. This is 2 is to 1 is to 2. Simple whole number ratio. This data is following the Gay-Lussacs law of combining volumes. Next, Avogadros hypothesis. Avogadros hypothesis. This is our last law in laws of chemical combinations. So, at constant temperature and pressure, equal volumes of all gases contains equal number of moles and equal number of molecules. At constant temperature and pressure, at constant temperature and pressure, equal volumes of all gases contains equal number of moles and molecules. But if the statement is equal number of atoms, this is wrong. May or may not be equal. So equal volumes of all gases contains equal number of moles. This is always correct. Equal number of molecules. This is always correct. Equal number of atoms may or may not be correct. For example, I am taking one volume hydrogen gas and one volume oxygen gas, one volume ozone and one volume helium. Different gases I am taking. So according to Avogadros law, at constant temperature and pressure, so their molecules are equal and their moles are also equal. So what I can write, number of molecules of hydrogen, number of moles of hydrogen is equal to number of moles of oxygen, that is equal to number of moles of ozone, that is equal to number of moles of helium. Moles are equal. And their molecules are also equal. Molecules. So the molecules of hydrogen is equal to molecules of oxygen, that is equal to molecules of ozone, which is equal to molecules of helium. But atoms are not equal. How do you find atoms? How do you find atoms? To find number of atoms, number of atoms is equal to number of molecules into atomicity. Number of molecules into atomicity. So let us say these molecules are X molecules. All molecules are equal. That number is equal to X. Then how many atoms are there? So number of atoms is equal to number of molecules into atomicity. How many atoms are there in the given molecule? So here the number of atoms are, in this case, number of atoms are, in H2 molecule 2 atoms are there. Total number of molecules X. This is 2X. This is also 2x, but in ozone 3x, in helium x only. So the total number of atoms depends on the atomicity. So according to Avogadros law or Avogadros hypothesis, at constant temperature and pressure, equal volumes of all gases contains equal number of moles and equal number of molecules, but not equal number of atoms. If atomicity is same, atoms also same. If atomicity is different, atoms are different. Now this is a relation. Volume is directly proportional to moles. Then V1 by N1 is equal to V2 by N2. So this is helpful for solving some numericals. So one question is based on Avogadros hypothesis. If equal volumes of helium, oxygen and nitrogen gases are taken at the same temperature and pressure, which of the following statement is true regarding the number of particles? So what is our first statement? The number of moles in flask B is greater than flask C. So their volumes are same. Then number of moles of B is equal to number of moles of C. Is greater is given. This is wrong option. Second, total number of atoms in all the three flasks is same. This is also wrong. Because here how many atoms are there? How many atoms? Here X atoms are there. Here how many atoms? 2X atoms are there. Here how many atoms? 2X atoms are there. So number of atoms depends on atomicity. Their atoms are not same. This is also wrong. Next, third one. The number of molecules is same in all the three flasks. This is correct. Equal number of molecules with equal volumes. Next, fourth one is average velocity of molecule is identical in all flasks. This is wrong. So average velocity means in kinetic molecular theory of gases you will study C average. Average velocity is equal to square root of 3 RT by M, where M is molecular weight. M is gram molecular weight or simply molecular weight. So average velocities depends on molecular weight. Their molecular weights are not same. Helium molecular or atomic weight is 4. Oxygen molecular weight is 32. And nitrogen molecular weight is what? 28. The molecular weights are not same. Their average velocities are not same. So third option is correct. Next problem. This is also one of the very important problem based on Avogadros hypothesis. At the same temperature and pressure, two flasks of equal volume contains nitrogen gas and ozone gas respectively. If the flask containing nitrogen contains a total number of X atoms, how many total atoms are present in the flask containing ozone? So here we have two gases, nitrogen and oxygen. What is given here? What is given here? Volumes are same. Equal volumes. So equal volumes means their moles same and molecules same. Their moles are same and molecules also same with equal volume at constant temperature and pressure. Next, what is given here? Total X atom. Nitrogen contains X atoms. Here X atoms are there. Here how many atoms are there? How many atoms are present in ozone? That is our question here. Right. So I am taking number of atoms of nitrogen divided by number of atoms of ozone. So number of atoms formula. What is that formula? The molecules into atomicity. Molecules of nitrogen into its atomicity 2. And molecules of ozone and its atomicity is 3. So as per the Avogadros hypothesis, molecules of nitrogen, molecules of ozone same and that is cancelled. And number of atoms of nitrogen is given as X. I want number of atoms of ozone. Number of atoms of ozone, how much it is? 3x by 2. So 3x by 2 means 1.5x. So second option is correct. Important problem from Avogadros hypothesis. So there are two flasks, A and B. Flask A 500 ml. Flask A 500 ml. It contains methane gas. Temperature 300 kelvins and pressure is 2 atmospheres. Flask B contains 1000 ml. Its gas is C2H6. Temperature 600 kelvins and the pressure is 1 atmosphere. What is the relation between total number of molecules in the two flasks? So to find the number of molecules, first let us find number of moles, because moles is equal to number of molecules into Avogadro number. Number of molecules into Avogadro number. So to find number of molecules, we should know number of moles. So here ideal gas equation PV is equal to nRT. So pressure is given, volume is given, temperature is given. So to find number of moles, we can use ideal gas equation. So throughout the chemistry, this JE level, Neet level chemistry, the gases are considered as ideal gases. In thermodynamics, few problems they mention that a gas is a real gas, or some of the questions from gaseous state they mention that it's a real gas. So except those few cases, in all the cases, any gas is considered as ideal gas for solving numericals. Right. So this is ideal gas equation. To find number of moles, N is equal to PV by RT. What is the pressure here? 2 atmosphere. Volume is how much? 500 ml. And R is gas constant. Temperature is 300 kelvins. So this is what? 1000 by 300. This is number of moles of A. Now let us find number of moles of B. PV by RT. Pressure is 1 atmosphere. Volume is 1000 ml. And temperature is 600 kelvins. So this is what? 1000 by 600. Number of moles of A 1000 by 300. Number of moles of B 1000 by 600. So whose moles are more? A moles are more. How many times it is more? 2 times more. So number of moles of A is 2 times of number of moles of B. Right? Now molecules. The molecules of A is equal to 2 times of molecules of B. Right? This is Avogadros hypothesis, important example. So all laws of chemical combinations are completed. Now the combination of, or by studying all the laws of chemical combinations, Dalton introduced one atomic theory to explain the structure of atom, and this is the first theory introduced to explain the structure of atom, that is Dalton's atomic theory. So here 4 important postulates are there. Of course, for each and every postulate, limitations are there. First postulate is what? Matter is indivisible. But practically matter is divisible. Matter, smallest part of the matter is what? Atoms, according to Dalton. But what is the smallest part of matter? Electrons, protons, neutrons, subatomic particles, neutrinos, mesons. So there are so many subatomic particles. So atom can be divided, and there are further smaller particles in the matter, not atoms. That is limitation. Second postulate is the atoms of same elements properties are same. Atoms of different elements properties are different. That is the second postulate of Dalton's atomic theory. So even for this postulate, there is an exception. For example, I am taking isotopes. Carbon 12, carbon 13, carbon 14, 3 isotopes. All are same elements, carbon, 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 but their atomic mass is different. Atomic mass is not same. The element is same, The atoms are same, but their masses are different. So isotopes is an exception for second postulate. Similarly, I am taking isobars. Isobar. So isobar, calcium 40, calcium 2040, argon 1840. So there are different elements. Calcium, argon, different elements, different atoms are there, but their atomic mass is same. So Dalton atomic theory says that atoms of same elements, all properties are same. Atoms are different elements, all properties are different. But in isotopes, same elements are there, atomic mass is different. In isobars, different elements are there, atomic mass is same. So this is a contradiction for the second statement. Now coming to third statement. Compounds. Atoms combine in a fixed ratio to form compounds. Right. So atoms are combining in a definite ratio to give compounds. This statement is correct. But what is the limitation? So why these compounds are formed? What is the need? What is the need to form compounds? Not explained by Dalton's atomic theory. That is limitation. Next, reactions. Reactions. So in simple words, reaction is nothing but what? Reorganization. Breaking of bonds and making of bonds. Breaking and making of bonds. For example, CH4 combines with oxygen, it produces carbon dioxide and water. So how this chemical reaction takes place? So the bonds present in the methane and bonds present in the oxygen are going to break. Breaking of bonds in reactants. Next, new bonds are formed in carbon dioxide and new bonds are formed in water. That is formation of bonds. Right? Simply it is a rearrangement of bonds, rearrangement of atoms. So chemical reactions nothing but it's a reorganization of atoms, right? So it is perfect, right? But what is the limitation in this? So why chemical reactions are taking place? Why chemical reactions are taking place and why compounds are formed? So in chemical bonding we studied that compounds are formed to get stability. Even chemical reactions, it's a struggle to get stability, right? So, but why compounds are formed, why chemical reactions are taking place, that is not explained by Dalton's atomic theory. What are the limitations here? These are NCERT limitation. So, Dalton's atomic theory could not explain gaseous volumes. So, nitrogen, suppose 1 mole of nitrogen is there, what is its volume? 1 mole of oxygen is there, what is its volume? So, gaseous volumes not explained and could not explain why atoms combine. So, that is another limitation. Now, important questions based on Dalton's atomic theory. Which of the following statements highlights a major limitation or modification of Dalton's atomic theory in light of modern scientific advancements? See, one by one, all statements. So, which is the limitation for Dalton's atomic theory? First statement, atoms of a given element are identical in mass and properties. Atoms of given element are identical in mass and properties. This is the statement of Dalton's atomic theory, but it is a limitation. Chemical reactions involves only the separation, combination or rearrangement of atoms. This is postulate of Dalton's atomic theory, but in this statement there is no limitation. But what is the failure of Dalton's theory? It could not explain why chemical reaction takes place. Third one is matter is composed of tiny and indivisible particles called atoms. So according to Dalton's theory, atoms are the smallest particles. But today we have seen so many smaller particles than atoms which are present inside the atom. So that's why they are called subatomic particles. So here limitation is there. So both A and C are limitations for Dalton's atomic theory. Next one, which of Dalton's original postulate is directly contradicted by the modern understanding that elements can exist as isotopes? So atoms are indivisible particles, there is no relation. Atoms of a given element are identical in mass and properties. Here limitations. So atoms of the given elements identical in mass. No, in case of isotopes, their atomic mass is not same. So second option is correct. These two are wrong. So choose the incorrect statement about Dalton's atomic theory. This is 2024 JEE mains question. Compounds are formed when atoms of different elements combine in any ratio. any ratio is wrong. So the elements are combined in a definite ratio, in a fixed ratio to give compounds. So first statement is wrong. So remaining statements are correct only. So they are directly postulates of Dalton's atomic theory.